So good morning, everyone. Today we'll be presenting our presentation. Today we'll be presenting the paper Meta-Q Learning. The original authors of the paper are Russell Fakur, Pratik Chaudhary, Stefanos Soato, and Alexander J. Smoller. This paper is originally presented at the International Conference on Learning Representations on 2020. Today, me, Apan Dostidar, and my classmate Mohammad Rashidul Haq Rashid will present this paper. So the contents of our presentation will start with the motivations behind this work, and after that we will discuss very shortly the contributions, and we will give a brief example on how meta-reinforcement learning works on a real robotic setup. After that, we will thoroughly dive into the Meta-Q learning, which is the core topic of today's presentation. So we divided this part in three different phases. So first we will discuss about the problem formulation, then how the multitask training phase used for doing the meta training in Meta-Q learning, and how the adaptation part works when a new task is introduced to the agent. After that, my fellow presentation mate will take over the presentation, and he will thoroughly discuss about the experimental setup and results analysis, and we will finish our presentation with the discussion at the end. So what is the motivations behind this work? The recent surge in meta-reinforcement learning research comes from applying meta-reinforcement learning techniques or general reinforcement learning techniques in real robotic setup. So the real robotic setups are very complicated and their operation are highly expensive, which hinders like extensive dataset building for doing reinforcement learning. Also, real-world scenarios are often cluttered with unforeseen perturbations, which violates the physics of the simulation environments, and all kind of real-world scenarios cannot be replicated in a simulation environment. So this creates a urge to develop meta-reinforcement learning so that we can adapt to a new task while exploiting the meta-train policies. Also, the authors have found that if we apply a non-meta reinforcement learning algorithm, we modify to the context variable, that is a representation of the current trajectory, it can give a promising performance compared to the current meta-RL algorithms. So if we compare the TD3 context with two meta reinforcement learning algorithms, one is MAML and one is PEARL, we see that TD3 context has given promising performance for 4 different control benchmarks. So what is the contribution behind MQL? So this research work has introduced an off-policy Meta-Q learning algorithm that efficiently utilizes the simple meta-training procedures of only maximizing the average reverse across all training tasks based on a multi-task training objective. Secondly, there is no requirement of doing exhaustive meta-training of action mapping policies. Instead, a simple approach that is incorporated with the latent representations of trajectory showcased a better performance. And a propensity estimation score has been proposed here for doing the adaptation technique for learning new tasks through exploiting the experiences stored in the meta-training buffer. So let's discuss about meta-reinforcement learning first. So the real motivation behind reinforcement learning is to learn from my old mistakes and do a better planning ahead. So in meta-reinforcement learning, we incorporate meta-learning with non-meta reinforcement learning. And instead of learning only one single task, we actually train a meta policy that can perform well on a class of tasks or a pool of tasks. So the objective of meta training phase is to learn a representation of a meta policy that can maximize the reward or the average reward over all tasks. The task can be anything. So and this meta training loss, this LK theta is totally dependent on the method that is being followed. For example, in AML method, it follows the gradient-based approach to develop the optimization process. So we discuss about a canonical example. So suppose we have a robotic agent, a robotic arm, and it is trained to grasp different kind of objects. So if we see the training objects, they are geometrically and physically quite different from each other. And in the task object or in the test object, we introduce two different or two new kinds of objects to grasp. And the concept of meta-RL enables the robotic agent to exploit the learning it has achieved during the training to facilitate or to accelerate the new task learning. Now we can discuss about the Meta-Q learning. So first, let's set up a problem formulation for this task. So if we consider a Markov decision process for a specific task K with a transition dynamics or a system dynamics Fk, If we are at state xt and we take a action u theta xt, the system will evolve to xt plus 1, and we get a new reward rt based on our action on that particular state. And the objective of reinforcement learning is to maximize this cumulative gamma discounted future rewards, which is often referred to as q-value function. Q-value function actually expresses the utility of a particular action being on a state X. And in conventional deterministic policy gradient algorithms, this kind of optimization is solved through a couple optimization problem. And this couple optimization problem has two different parts. In the first equation, we see that the q-value function are optimized by minimizing the TD error between the actual q-value function and the estimated q-value function. And in the second equation, we maximize the rewards based on the policy. So we can see that the Q function or the critique function is parameters by the phi parameter vector, and the policy function or the policy network is parameterized by the theta parameter matrix. So the meta-Q learning is basically divided into two phases. The first is the multitask training phase, and the second phase will be the adaptation to the new task. So first we will discuss about the multitask training phase. So the core idea or the simple idea between meta-Q learning is that we can do a multitask-based training for doing the meta training in meta-Q learning. So if we see the meta training loss here, that is LK meta theta, we actually using the Q-value function for a particular task K, and the actions will be the u theta x and the state will be the x. So what we are doing here is that we are doing a multitask training, and we are maximizing rewards for all the tasks that is inside this training phases. And this optimization problem is solved by a non-meta of policy algorithm, that is TD3. So why we are actually replacing a gradient-based approach like in ML with multitask training? So adaptation is in a gradient-based approach appears at the cost of underfitting on tasks. But if we say at multitask training does not suffer from an underfitting. Rather, it maximizes its performance on all the tasks, which accelerates or expedites the adaptation goal of meta. And additionally, we also learned a hidden variable, which is often referred in the paper as a recurrent context variable ZT. And our policies and our action value functions not only depend on the state and the action and the actions, it also depend on the context variable. And this context variable is estimated or learned through a created recurrent unit. So let's look at the pseudocode of the multitask training phase. So we start with a training task, that is the meta. We initialize our replay buffer and a initial parameters, that is theta. And we sample a task T from our pool of meta tasks. We gather data for the task T using our policy pi theta. And we also learn the transition, the transition representation, that is Z, through the context GRU, and add this experience or this trajectory to the replay buffer. So we then sample a mini batch from that replay buffer, and with that replay buffer, we update our theta using the optimization following a TD3 algorithm. And when the algorithm converges, we save this theta in our theta meta representation or theta meta policy representation, which will be used for the adaptation to the new task. And then we move forward to the next part, that is the adaptation technique for a new task. So this part is also divided into two parts. In the first part, we assure that the new for learning the new task new, while we are learning a new parameter representation theta, that should not diverge largely from the theta meta. So the difference between theta and theta meta should not be large. So it actually assures that it reduces the variance of the model while learning the new task, and it ensures the sample efficiency. So if we see the quadratic penalty term in the first equation, so it actually ensures that the theta should not diverge or should not differ much from the meta policy representation that we already learned. And in the second step, we actually introduced a importance weighting technique through calculating the propensity score between between the d new and the d meta. So d new is a new task, and d meta is the pool of tasks that has been used for doing the meta training. So this beta is actually calculates the odds or the probability of a trajectory theta that either belongs to d nu or d meta, and it actually calculate the importance ratio by fitting d nu and d meta on a logistic classifier, where z theta, that is the hidden representation, works as a feature space for this logistic classifier. We also have a second term that is lambda, and lambda is a function of ESS. ESS is referred to as the effective sample size. So ESS can be defined as a similarity between the new task and the old task, or the new task or the meta task. And if the two distributions are quite equal, then the value of ESS is close to 1. Otherwise, the value of ESS is close to 0. So the purpose of lambda is that it relaxes the penalty function. So if two two distributions or two tasks are quite equal or quite similar to each other, then the effect of the penalty term actually minimizes in the whole optimization process. So we can now discuss about the algorithm 2, that is the adaptation phase. So we have the new test task, that is T. We have a meta training replay buffer, and we have a meta train policy, that is theta meta. And we have with this theta meta, we calculate some, we gather some data from D. So we have a replay buffer now for the test task. With this replay buffer, we first do the first phase of adaptation, that is, we optimize our new learning with the penalty term. Then after that, for doing the second phase, we calculate the beta through a logistic classifier, and we calculate the ESS through the beta calculation through these equations. And when we have the beta and ESS in our hand, we can do the adaptation through the propensity estimation or to the importance weighting. So this importance weighting actually reweigh the transitions, or reweigh the effect of the new task on the new learning. And the penalty term is always there, and it makes sure that the theta is very close to the theta meta. And when this algorithm also converges, we evaluate theta on our new rollout tasks, that is T. And if we get a promising result, then we can say that this adaptation is done. So the learning that we have in the meta training phase actually helps us to accelerate the learning for the new task. Now, my presentation mate, Rashid, will take over, and he will discuss about the experimental setup and the result part.
Hello, everyone. So I'll discuss the experimental setup. Let us first get familiar with the benchmark that were used for the experimental setup. So this paper considers 6 benchmarks, and these are namely the half cheetah forward back, Walker 2D param, and forward back. We go to the next slide. Half cheetah velocity, and goal 2D, and humanoid direction 2D. So as you can see, like each of them are incrementally more complex. Some of them have 100 trainings and 30 test tasks on them, and some of them had only test tasks done on them. So if we go into the next slide, we can see the algorithms that they used for the evaluation. So they used both state-of-the-art meta-RL and non-meta-RL algorithms. So they used these 4 algorithms for the evaluation, and we are going to see the results compared with TD3 and MetaQ learning. So in this figure, the yellow line is the result for the MetaQ learning. And if we see that on the 6 benchmark that we discussed earlier, the MetaQ learning outperforms most of the benchmark for the most of the algorithm for the most of the benchmarks. However, for 2 particular benchmarks, this end goal 2D and Walker 2D params, the MetaQ learning performs comparatively worse than Pearl. The main reason behind is that in here we are not considering any kind of context there. So that's why Pearl is performing better than MetaQ learning. So if we go into the next slide, so in here, so we are going to consider of policy learning with context now. So so the pink line that you see in the bottom in this figure is without context, and the green line that you see here is with context. So as you can see, when we introduce context into the MetaQ learning, the performance is comparative, almost comparative to Perl. So that shows the effectiveness of meta-Q learning without the complex state-of-the-art algorithm, just by introducing some context there. If you go into the next slide. So in here, we are basically evaluating some hyperparameters of the MQL. So the first, we are comparing MQL with TD3 context. So as you can see in here, even with the context, MQL is performing better than TD3. Then when we consider the propensity parameter beta there, as you can see, it's still the MQL adapts well with adaptive beta, and the same result happens for gamma. So the MQL adapts pretty nicely with adaptive beta and gamma. So if we go to the next slide. So now we are going to see some results for out of distribution tasks. So we are going to look into some medium difficulty environment and some hard difficulty environment. And so the initial training was done on some distribution parameter, for example, in here 0 to 2.5 and here 0 to 1.5. But the evaluation will be done on some out of bound task now. So for example, in here, 2.5 to 3 is chosen. So if we look into the result here, so we can see that meta-Q learning outperforms Perl significantly here. And like when you look into the beta and gamma, as you can see, the beta is quite less. So it basically shows that MQL automatically adjusts when the adaptation is new. For a new task, MQL adapts pretty nicely. If you go into the next slide, so the previous slide was for a medium difficulty task environment. Now we are looking into some hard environment. So obviously there are more noise in this figure, but still we can see that MQL is outperforming the TD3 context there, and the same issue with the same adaptation with the propensity and gamma is seen here. So this result basically show that MQL performs well in medium to hard environments. If you go to the next slide. So to summarize, this paper proposes a simplistic meta-RL approach based on 3 elementary but unique ideas. One is an off-policy Q learning incorporated with context inadequate enough to produce comparable performance. Next, only maximizing average reward of training tasks is a promising approach, which is more straightforward than state-of-the-art algorithms. Next, recycling data from stored replay buffer through an important weighing technique. Propensity score estimation, which proposes sample efficient algorithm. This paper also highlights the urge to create new and realistic robotic environment for further validation of meta-RL approaches. In future, we plan to validate this work through implementation into a real multi-agent collaborative robotic manipulators, research setup for addressing adaptive action planning in real time. We thank you for listening to our talk. Please reach out to us if you have any questions. Thank you.
Thank you.